Hey, good afternoon, everyone. What we are going to do today with this very short tutorial is to see how this reaction in organic chemistry is going to proceed. In the previous tutorial, as you noticed, we said that when we have structures like that and reacting agents within a solvent, which is shown on this arrow there, you have to always search for the elements that you're just going to show empty orbitals and also the elements that they show that they possess lone pairs of the electrons, which they are not part of the resonance hybrid structures. Then in that case, it becomes constrained. Then in order to do so, what we need to do for this part of the tutorial is that I'm just going to look into the left side of the arrow, which is going to be the reacting agent which I have there. On the first glance, which I look into this one, I can identify the presence of one of the elements of the 7 periodic table, which is going to be the bromide. We know that due to the tremendous difference of the electronegativity that exists between the carbon and the bromide carbon, the bound which exists over there, it's going to be highly polarized. Almost all of the electron clouds is going to be pushed towards the bromide and give it a partially negatively charged. And the presence of the solvent that we have, which is going to be the ethanol, which is C2H5OH, enticing the formation of the bonds between the oxygen and the carbon, which is going to be left alone in the absence of the bromide. Then what it happens here is that due to the reduction of the transition energy in the presence of this polar product solvent, the bromide is going to act as a very good leaving group. It's just going to end up somewhere there with the lone pairs of the electron, which takes completely in this heterolytic bound cleavage to get the negative charge there. What do we end up here is this. We have the carbon, which is there, this methyl group, which stands on the left side, this methyl group, which stands on the other side. And also, we remember that because carbon has to be in the octet format. The octet format means that it has to be have full electrons like the 8 electrons at its valence shell. Then as a result, we have the presence of the hydrogen here, which we didn't show this on the left side. Now, the bromide is gone, then we are left with these structures. On the previous tutorial that we saw, we noticed that when we have structures like that, what we need to do after any bound dissociation or any bound formation, we have to stop and find the formal charge associated with those elements that they were directly impacted by either the dissociation of the bonds or formation of the bonds. The element which is directly impacted is the carbon, central carbon here, which it means that we are just going to draw our net around this and find the formal charge. The first question that we need to ask ourselves in order to find the formal charge is that, say, okay, what is the address of the carbon? And by the address, we mean that the group that it belongs to on the periodic table, which is going to be group 4. Then the next crucial question that we have to ask is that how many electrons I can find within the net which I have thrown. I have 1 electron here, I have 1 electron there, and 1 electron there. Now it becomes 3. Then 4 minus 3, I get the +1 over there, which in that case, what it means that the formal charge of the carbon over there for us is going to be essentially +1. And that's essentially the formation of the carbocation, which we have there. Also, I have to denote here that the carbon which we have there is the secondary carbocation. Then we have to also be careful about the formation of the carbocation, but we assume that the reaction proceeds in the formation of the carbocation, which is a kind of an electrophile, means that it's looking for the electrons inside the environment that we have. Now, we form the secondary carbocation here, but at the same time, we are noticing the presence of another reacting agents, which is going to be sodium ethoxide. As we showed that on the previous lecture, when we have the sodium ethoxide, which is C2H5O and A, in the presence of the solvent that we have, which bears similar structures as C2H5 of the sodium ethoxide, in the presence of the solvents, the ion is going to be dissociated, which means that we have C2H5O. Now, in the fight between the lone pairs between the sodium and the oxygen, because sodium belongs to the group 1 of the periodic table with the very negligible electronegativity, that in fight between the sodium and oxygen, in order to see who is going to faster, the electrons, when it's going to be dissociated from the bond, electron is going to win, then it's going to be negatively charged, and sodium, which is dissociated, it becomes positively charged. Now, then as a result, what we may end up here is this. Now we have the ethoxide here in the solvent find itself in close vicinity to the carbocation which we have formed, with the negative charge, which represents it's an incredible strong Lewis space. Now, what we may end up here is this, that we say that, okay, now we have a very strong Lewis space. It is very strong in terms because it carries 3 lone pairs of the electron and full negatively charged. Then what do we expect is that the nucleophilic attack happens and we form an ether there. But the key thing that we have to be careful here is the presence of this thermodynamic sign, which it means that the reaction that you are conducting is in a high temperature. You are not conducting this reaction in a room temperature. Then in the heat which is supplied by there, you expect that you just have an elimination reaction. But what elimination reaction we may expect? The first thing is that the CH3 that we have over there, it essentially can form something like this structure, which you can show the hydrogen showing at, let's say, in an expanded format of the hydrogen which we have there. Now, when you have these structures there in the presence of the heat, as a previous tutorial we discussed, one of these hydrogen, you are providing enough energy that lose this environment, the contact between the carbon, and also the contact between the carbon, and also the hydrogen is going to be extremely loose because of the heat that you provided there. Then in the fight between the hydrogen and carbon, in terms of the fostering of adopting the electron bonds between the carbon and hydrogen, carbon is going to win because it has a high electronegativity, and hydrogen is going to just go outside in terms of the hydrogen ion, which is simply a proton in the solvent. Then what we may end up from this structure is this. We have the carbon which is there, the central carbon, which is positively charged. We have the methyl group which we have there. We have the hydrogen which is there. And also, we have the carbon, which is now connected with 2 hydrogen and carries a lone pair of the electron in its valence bound. Then the thing is that now we just dissociated the bond. We are just going to find the effective charge. For the effective charge, we are just going to look into the carbon and we ask 2 important questions. The first question that we are just going to ask is that, what is the address of the carbon on the periodic table? We just come to group 4. And when we count the number of the electrons around the carbon, when we draw our nets around that, we see that we are looking for 5 electrons. When you subtract it, you get the negative 1, which denotes the presence of the carbanion, which is a carbon which is negatively charged. Now, which is going to be very unstable. Then you have to kick out the cause of this instability, which is these lone pairs of the electron. Then you can do that in order. The only way you can possibly do is that you kick these lone pairs of the electron to form a double bond between these 2 carbons, which in that case, if you follow this structure, you see that you get this carbon, which had this methyl group there. I'm not going to show the hydrogen there, but I'm going to show a double bond there. Then we have CH2, which is going to be the format that we have formed in this structure, which is going to be an alkene structure, as the previous tutorials that we had. Now, this one, you may also, for the final points that we may discuss, you may ask yourself, why possibly I didn't dissociate this hydrogen from this carbon which I have there. You see that if you do that, you get the exact similar thing, which becomes extremely symmetric. Then there is no big distinctions between this carbon, hydrogen, or this hydrogen. Then they are both equally possible. But the third question that you may ask yourself is that why you didn't subtract the hydrogen, which is directly connected to this carbocation. If you do so, for two reasons you cannot do that. First, you need extreme energy. And the second thing is that if you just detect, for example, this hydrogen, you are forming with the carbon, which has two positive charges there, then it becomes extremely thermodynamically unfavorable. Then the direction doesn't proceed that way. Then the only possible removal of the hydrogen due to the presence of the heat is the hydrogen, which is either connected to this beta carbon or this beta carbon. Because you remember, we call these carbons, which is directly connected to this carbocation, beta carbon. Then you see that the possibility to remove the hydrogen is surrounded by these two beta carbons and not this hydrogen there. Then as a result, you get a symmetrical alkene if you remove the hydrogen from this beta carbon or that beta carbon. And that forms these final products of our reaction. As a final point, I'm just going to remind you one last important thing. If the heat was not supplied, you just follow the simple nucleophilic substitution. But because of the heat is present there, the form of the reaction is going to change. And you're just going to have a dominant product, which is going to be the alkenes in the environment. And the final point, the bromide and the sodium also is just going to form the sodium bromide solvent in the solvent that we have there.